my name is Yvonne Granfeldt, and I will be the chairperson during this PhD defense. And I am from Department of Food Technology, Engineering and Nutrition. And this is a hybrid meeting, as you have already known. And beside the people, us in this hall, we have people online in Bolivia and in Sweden. I will start presenting the actors in this room and then hand over to Professor José Bravo, chairman at Universidad Mayor de San Andrés in La Paz, Bolivia. So, especially welcome to faculty opponent, Professor Matteo Marangon.
Thank you.
Yes.
Thank you.
University of Padua in Italy.
Yes.
Yeah.
Yes. Thank you. It's a pleasure to be here.
Yeah, thank you.
Having me.
And I will soon give the floor to you. Yeah. And then we have the examination committee. We have Dr. Mats Lehmann from Skåne University Hospital. And we have Professor Anna Ström from Chalmers University of Technology. We have Deputy Member, Associated Professor Anne Nilsson from Lund University. And finally, Professor Yannis Kronakis. Is that okay?
Yes.
From Technical University of Denmark. So, we are most grateful that you have taken this assignments as opponent and member of the committee, and we are grateful for that. Thank you. And I also want to present Daniel's main supervisor, Björn Bergenstål. We have here, and he is from the Department of Food Technology, Engineering and Nutrition. Now I hand over to José Bravo at the Universidad de Mayor San Andrés. No, the Universidad Mayor de San Andrés. Are you there?
Good morning to all.
Morning.
My name is Professor José Antonio Bravo. I'm current chair of the Chemical Research Institute of Major San Andrés University at La Paz. It's a great pleasure and a great honor to be present in this occasion for the PhD degree dissertation of Mr. Daniel Osorio. And immediately I proceed to the introduction of the candidate for this PhD degree. At my left, Mr. Daniel Osorio, and his supervisor during this long work of research that involved the Chemical Research Institute and the Food Chemistry Department of Lund University, Professor Mauricio Peña-Rieta, charged of the supervision, as I already said. Thank you very much.
Thank you. Thank you. And the agenda for today will be the following. So Daniel will start to give a short presentation of his thesis, and then Professor Marangon will give the statement of the relevance for the thesis. And thereafter, Professor Marangon will start the question section with questions and discussions about the thesis. When that has finished, I will give the examination committee the opportunity to ask questions. And finally, the audience, both here and online, to ask questions before we close the defense. So, I think that Daniel, you can start. Can you share the screen with us?
Okay, I will start with this. So I need permission for sharing the screen.
Can you ask him try again because
Okay.
He is a panelist.
Can you try again? You
Yeah.
should be able to do it.
Give me 1 minute.
Yeah.
Oh.
He's a
This is the one. Hasta que iniciar. Primero. Wait me, please. Something is. Pero ahora, ¿cómo voy a? Pero tengo que share con el Zoom. Share. ¿Por qué no está? Esta. ¿Esta? ¿Cuál, por ejemplo?
La segunda, debajo de la.
No, eso no es, solo hay dos screens.
Sí, cualquiera de las dos.
La una.
Yes.
Yes?
Yes.
Can you see it now?
Hasta tus diapositivas. Sí.
So, can you see the presentation now?
Yeah, we can see it.
Do you hear me also well?
Yeah, we can hear you.
Okay, perfect. I will start. So thank you, everyone, and welcome to my presentation, my thesis dissertation entitled Asymmetrical Flow Field Fractionation in the Separation, Characterization, and Application of the Wine Particle Matter. My name is Daniel Osorio, and I'm from the Department of Technology, Engineering, and Nutrition. So first of all, I want to define what is wine particle matter. The wine particle matter refers to the largest particles in wine. So they can be classified as a wine colloids, which are made up of condensed tannins and proteins, and also can be classified as a wine macromolecules that are made up by polysaccharides. The content of this.
Sorry, Daniel. We can't see you in the presentation mood. We can't see the presentation. Can you try to do it so it's a bit bigger?
I think people here can watch my presentation.
Yeah, we can see it, but we see two figures. Is it okay?
Yes.
Yeah, it's okay. So then continue, sorry.
Okay, and I will continue. So just let me know if something happens again, please. And we will fix it. So I was telling that these larger particles and the wine particle matter is composed by wine colloids and by wine macromolecules that are made up by condensed tannins, proteins, and polysaccharides. And the content of these compounds can vary according to the grape variety, to the vinification techniques, and to the methods used for the detection. So the origin of these compounds are mainly endogenous. Since these compounds are part of the grape berries, they are present in the skins, in the seeds. They can be also released by microorganisms during the vinification. They also can be added during the vinification or to the winemaking. So why these components are important? Because of their physicochemical properties. For instance, in white wines, we have the phenomena of stability and instability and the haze formation that is related to the heat and stable proteins, and which also affects the color and the clarity. In red wines, we have the phenomenon of polymerization and precipitation, but also we have another property related to these larger compounds as organoleptic sensory properties, and mainly the astringency. So here we can observe how these larger compounds are bonded together by either forces or by hydrogen bonds, and possibly with covalent bonds also between the flavans and the proteins. So all these interactions are in function of the size of these compounds, of the concentration, which affects the properties I've shown, but also the solubility. So that is why it's so important to find methodologies to be able to isolate, to separate, and characterize these properties. And therefore, my main objective is to evaluate if the asymmetrical flow field fractionations can be a suitable tool to fractionate the particle matter and also to characterize the separate fractions. So the specific objectives that supports my main objective is to characterize the phenolic content in red wines and evaluate the factors that can affect the phenolic profile and the possible particle formation, which is studied in paper 1, to develop and optimize a methodology of separation for the wine particle matter, testing different properties, different separation, and using the and to establish a macromolecular and specific characterization using the online detector. To apply this methodology developed during the vinification technique, precisely in the clarification process and the white wines, and to apply this methodology in the red vinification using different grape varieties and also different stages of the fermentation. So we go to the method section. So the first methodology we use, and the most important during the process, was the asymmetrical flow field fractionation. So we use this technique because it shows some advantage over different separation techniques. It provides a wide separation range of sizes. As you can see, the sizes that we can separate goes from 1 nanometer to 50,000 nanometers. The wine is around 1 nanometer to 30 nanometers. This technique offers a gentle separation mechanism with low shear forces, which means that when the sample is separated, it is not degraded, but also it offers the possibility of fraction collection. So here we have a scheme of the mode of separation of the channel, the open channel in the DFF. I will be very brief to explain how the separation occurs in the channel. So first we inject the wine sample, and then a perpendicular force called cross flow pushes the samples towards the ultrafiltration membrane of 10 kilodaltons. So the smaller particles are dragged through the membrane to the waste. And then by diffusion, these samples are contracted automatically, and occurs the process of relaxation. And when this equilibrium is reached, the sample is ready to be eluted. And by the parabolic flow, the sample can start to be eluted by the main pump. And then the particles of the samples are separated thanks to the hydrodynamic radius differences. We have another methods that has been used to support the characterization, and which are based in the UV, MOS, and DRI only detectors. We have the determination of the hydrodynamic radius, which is based on the retention time, which gives us the size. We have provided the apparent density, which tells us how dense is the fraction or the particles within the fraction. We have two new properties that wasn't previously calculated with this online detector, which is the concentration, which is based in the DRI area of the peak, the flow of the channel, the injection volume of the sample, the refractive index increment of the peak. We also provide the specific absorptivity, which tell us how much UV light can be absorbed in the fraction compared to their concentration, and normalized to the same ratio of the BCA standard. So we have other methods that we use to support this characterization. We use the total antioxidant capacity determination and the phenolic content. And we also measure some common enological parameters as the protein content, the stability, and the turbidity. So we have the result sections. The first results for the first paper that relates the characterization of the phenolic content and the saccharides that affect the phenolic profile. In bottled red wines, we can observe that 2 HPLC chromatograms, one for the resveratrol identification and other chromatogram for the monosaccharides identification, both compare with the external standards. Also, the results of the antioxidant capacity and the phenolic content and the total flavonoids were plotted all together against to explain in just one plot, the PCA by plot. So here we obtain a result that is interesting for us. We can observe a cluster that is formed by the high altitudes, which correlates positively with the resveratrol content, with the total flavonoids, and with the antioxidant properties. So that's telling us that the high altitude has an impact over the phenolic content of the wine. And this is a result that we have used for the sampling for the next studies, where we consider the phenolic content and the particle formation in the one colloidal fraction. So this is our main result in the paper 1, and we can follow the results section to the paper 2, where we develop the separation methodology of the one particle matter using the asymmetrical fold fractionation. So here we can observe 3 different fractograms for 3 different Argentinian red wine samples that are from the high altitudes, around 2,000 millimeters above sea level. So here we can observe clearly that we have differences after the fractionation in the signals. But what these fractograms tell us is that, so how we can interpret these fractograms. So basically we have the x-axis, that is the elution time. In the y-axis, we have the molecular mass and the hydrodynamic ready, that is related to the black dots and the pink dots respectively. But also we have 3 different signals: the UV signal in green, the DRI signal that is proportional to the concentration in blue, and the multi-annualized scattering, that is the red signal. So here in these 3 different fractograms and for the 3 different samples, clearly we can see that there are differences in the patterns, but also we can see that there are only 2 populations that has been fractionated. And the first population is classified as a wine colloid since they show high UV absorptivity. So therefore, the second population is classified as a wine macromolecules because they don't show UV absorptivity. And we can see here also that, for instance, in the DRI signal, for instance, we have a higher concentration in the one macromolecular fraction compared with the other samples. But to get a complete characterization and the complete values and interpretation of these fractograms, we have applied the formulas that I showed before. And I will show the table result for the whole set of samples. So here we can observe the table results for the whole set of samples that covers Cabernet Sauvignon, Malbec, a mix of Malbec and Cabernet and Tannat. And we can observe the macromolecular characterization for the hydrodynamic radii, the molar mass, the apparent density, and the specific absorptivity. We observe the values for the one colloid population 1, and for the macromolecular population of population 2. So we can observe clearly here the differences between the properties between each of the populations. As for instance, we can see as an average of the values that the population 1 in the one colloids, the one colloid population 1 in the hydrodynamic radii or molecular weight properties are much lower. So the samples are shorter and lighter, while the one macromolecular fraction is longer and heavier. And opposite to this, we can see the apparent density and the specific absorptive properties. The one colloid fraction is much denser, and it shows a high absorption of the UV light. So we can follow this second table. Also, we have obtained during the characterization the values of the refractive index of the total solids of the one colloidal fraction, the absolute concentration for each of the peaks. So where we can observe also different values between the samples and between the fractions. So the results for the fractionation and the characterization can tell us that there are two main populations in the one particle matter, and these two populations show different properties, and also these values changes among the samples and the gray varieties that are related with other factors, possibly during the vinification as well. So we have to now apply this methodology of fractionation and characterization to the winemaking process, precisely to the clarification process in white wines. So this is their paper number 3, the results. So here we can observe directly and with same concept, a fractogram of the white wine that it was not clarified. So this is a wine that was previously, or a raw white wine that was previously, that it was in the middle of the process. So here clearly we can see 3 populations. And these 2 first populations, according to the definition we had in the previous study, we can classify these 2 first populations as a one colloids that absorbs UV light. And since they are white wines, we assume that they are composed by proteins, and these proteins that are heat unstable. So this is why we need to clarify. So then we have clarified the sample, and we have clarified with activated bentonite, a clay. So we can see clearly that after the clarification, the elution profile of the signals is different. It's clearly that the UV signal has almost completely removed, and also the population 1 in the DRI signal, in the blue signal, also almost has disappeared. So other results we have after the treatment with the synthetic polymer, PVPP. And here we can observe, for instance, that the 2 first populations did not change too much, while the third population, or the macromolecular population, it has been reduced in the concentration. We follow the blue line, or the DRI signal, which can be interpreted that this synthetic polymer has more affinity for the macromolecular fraction. But also we know that this synthetic polymer PVP is widely used for removing phenols, but the soluble phenols that are present in the wine. And then we use the vegetable protein of potato to clarify the sample. So in this fractogram, we can observe by the DRI signal in blue and by the green signal of the UV that the fraction has been removed, both in the 3 populations, but also we have some material that has been remained, which, so we can interpret this that some of the material has been removed, but also some of the properties of the wine still. And I think this is comparable with the first activated bentonite treatment, where we can see that this activated bentonite, it was a very strong treatment, that it removed a lot, where it could just remove a lot of the characteristics and properties of the wine. So we have observed the 3 different processes, but we have used like 8 different clarifiers in different doses, or 6, and we can observe but also we have created the same data, and we have used we have analyzed the phenolic content, the protein content, and other enological parameters in these wines, and we try to correlate all these variables all together to see how this removal clarification process can affect to other properties. So we have plotted all these results together in a PCA figure to interpret these results. So this figure can be interpreted in the same way, but for instance, we have the raw white wine, the unclarified wine, here in the left side of the corner in orange. So after the clarification, we see how the clarified wines have grouped together according to their properties. For instance, in red, we have the synthetic polymers. And then in purple, we have the clarification, use the bentonite or the clay in different doses. In green, we have the vegetable proteins. So together with us, there are clusters formed with the other properties. So here we can interpret in different ways, but one easy way to show is, for instance, in PC1, there are differences in concentration. That explains the removal concentration. So for instance, we have the clarification cluster of the synthetic polymers that correlates with the concentration of peak 1 and peak 2, which is telling us that after the clarification, this concentration remained the same. So opposite to this, we have a cluster formed by the removed fractions, concentrations, and other properties that correlates positively with the vegetable proteins. So PC1 can explain a little bit of the concentration removal, but in PC2 we have the variations of the doses used of the clarifiers. So for instance, we have here along to the PC2 how the treatment of the vegetable clarifier in different doses can affect different properties. So we can observe the variations of the different doses of the clarifiers along the PC2. And for instance, one property that is related to the different doses uses is we have used here the bentonite, and here a bentonite with higher doses that correlates with the stability in a better way in the total phenols, telling us that with this bentonite and with this dose of bentonite, we can get better stability. So this is the way how we proceed and how we apply the FF during the clarification process of the white wines. We have the results for the 4th paper that is related to the unification study of the red wine. So for that, we use 5 different grape varieties, and we focus in 5 stages of the winemaking. The first stage was the end of the lactic fermentation, the end of the alcoholic fermentation, sorry. The second stage was the end of the malolactic fermentation. We focused the 3rd stage in the clarification, and the 4th stage in the bottling and the cold stabilization, and the 5th stage, we took the samples for the storage and the aging after 6 months around. So this project started in 2019, and the last samples we took in 2021. So here we have a figure that shows how these properties, some properties, evolve during the winemaking process. Precisely the hydrodynamic rarity, the molecular weight, and the apparent density for the Tempranillo sample. So here we can observe the 3 populations. the two first population classified as one colloids, and the third population, the one macromolecules. And clearly in red, we can observe how the molecular weight has changed in their values along the winemaking from stage 1, 2, 3, 4, and 5. But in stage 5, also for peak 2 and 3, the end value was almost the same as the first stage. So we can see that the values have changed during the winemaking, but then at the last stage, these values tend to recover the initial value. On the contrary, for the apparent density, we have seen the same, we can see the same behavior, but only for population 3 of the macromolecules, where the stage 1 ends very close to stage 5, but not for population 1 and 2, which can be interpreted that some particles or some properties changes a lot during the winemaking, but others no. So we have also here another way to interpret this, but related to the operation units used during the winemaking process. So here we have the stage 1 and how this stage 1 affects the properties. We have the stage 2, the end of the malolactic fermentation, and we can observe how the concentration of the particle has increased due to the release of the components after the fermentation. And then we can observe the impact of the wine making over different properties with the clarification and with the bottling and the cold stabilization. We can observe how after the clarification and the cold stabilization, some of the properties have decreased, but also we can observe that after during the storage or the aging, the properties can, some of the properties, precisely the absorptivity, tended to increase again. So all of that can tell us that different grape varieties can behave different, but the vinification process has a lot of impact over the particles and properties of the wine. So we have to remember and discuss a bit what we have obtained in the different papers. In paper 2, we have separated two main populations and characterized. The first population was the wine colors that show lower values in the hydrodynamic ready and the molecular weight, but higher values in the absorptivity and in the apparent density, and it is constituted mainly by polyphenols, while in the wine macromolecular fraction, we see the opposite behavior of the properties. We show that they are larger and heavier, but with low density and apparent and specific absorptivity, and it's mainly composed by polysaccharides. Also, we have to say that in paper 3 and 4, 3 populations were fractionated or separated. And in the study of the white wines, the second population was classified as a part of the wine colors because of the UV absorptivity. But in the vinification study in paper 4, some properties, some grape varieties differs in the intermediate property. So we couldn't really classify the intermediate fraction as a part of the wine colors. We have to say that the methodology of the A4 coupled with multiple detectors allows to evaluate the removal efficiency when different doses of clarifiers are used, but also that this removal affects different properties of the wine, and all of that can be assessed by the asymmetrical flow field fractionation coupled with multiple detectors. In paper 4, the methodology have shown that it can track the particle formation and the changes that occur during the vinification. And this particle system is highly dynamic during the process, where some properties can increase and decrease during the process, and then can increase again, precisely the absorptivity. We also have to say that the methodology of the online detection is possible to analyze many samples in shorter times, determine different properties. And these properties agreed with previously or with the same property reported by other studies, but which can take longer times because we are using online detection only. So here we have a comparison table that how we can obtain similar data. For instance, in paper 2 and 4, we have obtained the incremental refractive index for the wine colloids of wine macromolecular similarly comparable to the ones that Pascotto has used in the publications. We have obtained the wine colloid fraction in the similar range, which other study that determines the total phenols concentration in the wine by Marassi, and the same in the wine macromolecular fraction. We have obtained similar data by data reported by Coelho and Marassi in the polysaccharide fractions that was comparable to our wine macromolecular fraction. So we have some conclusions. We can say that the phenolic content and the antioxidant capacity can be affected by several factors, and mainly the high altitude of the vineyards where are located, and this can affect the particle formation in the wine colloids fraction. We can say that the AF4 methodology coupled with multiple detector is a suitable technique for the separation and characterization of the wine particle matter, but using always a one carrier model as solvent. The macromolecular and specific characterization were based in properties as the molecular weight, the hydrogen ready, concentration, but mainly with the absorptivity together with the apparent density, because these both properties defines the nature of the fraction. So we can say that the application of the AF4 methodology allows not only for qualitative determination, but for quantitative determination, that this is a good advantage of our methodology. We can say that our methodology allows a full, rapid, and fast characterization of several samples at any stage of the vinification, but the incremental refractive index Dndc value should be determined in a separate experiment, and we use dialysis, but using the same conditions as we use during the separation in the FFF. We can say that this methodology allows to characterize different samples according to their macromolecular and specific properties, and the enological factors can be used to take decisions during the winemaking process to achieve a desired profile wine. We have the section of the future outlook. So we propose that this methodology needs for an extra online detection to support the characterization and the quantification. And this characterization also can be complemented by spectroscopic analytical techniques and methods, because the intention is to characterize and monitor uncharacterized compounds from the colloidal and macromolecular networks, from the class of wine, from the grapes to the glass of wine. So another way to use this methodology is to apply this methodology at any particular stage of the winemaking. For instance, we can evaluate different fermentation process using different types of yeast and bacteria, different fermentation nutrients or yeast strains. We can use longer time during the aging and see how this affects to the wines and how this can be represented in the colloidal and macromolecular fractions. During the clarification process, we can use the methodology to evaluate the role of different finished agents that we haven't used, like the zeolites or chitins or zirconium or carrageenan, and see the impact of this clarification over other enological properties. So we can focus on monitoring the wine macromolecular fraction. For instance, we can delay the harvesting of the grape berry and see how this affects to the macromolecular fraction. But the idea is to not only to track and to monitor the wine colloids and wine macromolecules during the vinification process. The idea is also to be able to control, if possible, to modify some of these properties, which can at the end have some possible consequences in the visual properties, in the colloidal stability, and in the final quality of the wine. So I have to give my acknowledgement first to the SIDA, the Swedish International Development Agency, of course, to Lund University, to my home university, Universidad Mayor de San Andrés. And I have to thank you also to my main supervisor in Sweden, Professor Björn Bergenstol, but also to all my co-authors, to my supervisor he's in Bolivia, that with the effort of everyone, this result cannot be achieved. So thank you very much for your attention.
Okay. Yeah. Thank you very much, Daniel, for this interesting summary of your thesis. And now I will give the word to Professor Marangon to give a more overview of the research field.
Thank you. What did I do? No, this one. Okay. Can you see it? Can you hear me? Daniel?
Not there. You need to share it.
I'm not sure. Okay, sorry, I wasn't sharing anything.
I can hear you, Mateo.
What should I do about this? I tried to share, ignore it. I don't want to touch it.
Pushing the cross.
Okay. No, I don't like that. Oh, maybe. Okay.
And now you're sharing the screen.
Daniel, can you see and hear it? Don't know if they can hear me. If I say fail to detect the speaker.
We can hear you very well, Mateo.
Oh, no, because I don't see what I'm seeing. Yeah, how they can.
No, they see this.
Yeah, no, but they don't
Okay.
hear me, I think, because I'm trying to see that error.
Where is that file?
Yeah, killed it. No, I think. Okay.
Yeah.
Does it work? No.
Can you hear us, Daniel?
Yes, I can hear you very well.
Select. Oof.
No idea.
No, but he could. Do you hear us?
Yes, we can hear you
Yes,
very
but we
well.
don't hear him speaking.
But where can we?
Should I take this off?
No, I would like to click the blue. Do you hear us, Daniel?
Yes, I can hear you
We
very
don't
well.
hear him. Oh, what's that possible?
I would like to clear that message, but it's gone. mean, this is correct. Ah,
What have we done? Don't ask. That's good.
I think it's just start.
hörs det ut?
Yeah,
Well,
yeah.
Okej. Då.
Just start. Show it that it's there.
Okay.
Yeah.
Okay. All right. Good afternoon, everyone. Good morning in Bolivia. Thank you, Daniel, for presenting all the amount of work that you've done in your PhD thesis. It's a huge amount of work. It's groundbreaking work, at least in the field of wine science. So I'm really pleased that I could have a closer look to that and get familiar with all the good science you did. So when Bjorn asked me what I should do, this is very unusual for me to give a presentation in a defense, but I try to talk a little bit about what is known and the importance that colloids have in wine science so far, and try to explain how that ties in with the AF4 technique, because I think there's a lot of potential there for the technique to be used in wine science. So just general overview, what is in wine? Well, there's a small stuff, the soluble, so the alcohol, the acid, the sugars, and monomeric phenolics. There's the colloidal particles, and I know that we're going to discuss about the definition of colloids later, Daniel, because in wine science, at least, no?
I'm really sorry.
It's not working?
Because the screen is not changing in Zoom.
Okay.
So we have to.
It's changing here, it's not changing in Zoom?
Yeah.
I think I know what the problem is, because it's usually that you share the wrong thing in Zoom.
Yeah. So we need to stop sharing.
Just stop share and let me show you.
I think it's me every time I come here. The thing that
No, I think it's us. So where are we in share screen? I think the only way to make it work is actually to share.
That's the presentation.
No, not to share the presentation. Klicka på den.
Men den kan. Yeah, that looks good.
I will go out and see if it works.
Okay. Did it change?
No.
Yeah. Okay. Okay. So I was saying, like colloids in wine, we have a slightly different definition or way of calling them compared to what they've been defined in the thesis. We refer to macromolecules as protein polysaccharides and condensed phenolics. So we keep the monomeric phenolics, the free form, outside of the colloidal definition. I don't know if it is the right one or wrong, but that's the convention. They have this intermediate size, and so they are important because they have many roles in winemaking colloids. They form stable colloidal dispersion that do not sediment, or unstable one. They tend to aggregate over time and cause problems, basically. So instabilities, which are linked to the shelf life of wine. And then we have the big stuff, cells, aggregates, crystals, stuff that normally get filtered away in a wine. So colloids / macromolecules, depending how we want to call them, in wine science, they play many roles. They've been studied for many properties they have. One of the most important ones is related to clarity and stability, and the thesis touched on that: clarification, stability, turbidity, because due to their nature, ability to aggregate, to meet each other, to grow over time, they can cause sediments, turbidities, and consumers don't want turbid wines. They are also important on the action of findings, so the addition of molecule to wine to remove a target molecule from the wine, like the bentonite or the PPP that was tried in the thesis. They're important for mouthfeel, to give, because they increase slightly the viscosity of the wine, and so they change the way that the wine moves in our mouth, and the weight of the wine, the body is also defined, so it's an important quality attribute. They play a role in astringency, especially the phenolics. They're astringent, but when they complex with other macromolecules, they are not able to bind to the salivary proteins anymore so well. And so they can modulate astringency, which is something, of course, a quality, positive quality for wine. They play a big role in color stability of red wines. The color in red wines is given by anthocyanins, which when they're free, in a free form, they're very red, very bright color. So young wines are very brightly red. Over time, they combine in certain condition with other macromolecules, namely phenolics, condensed tannins, but also polysaccharides. And so when they do this combination, when they aggregate with other phenolics, they become less red, but the color is more stable over time because the anthocyanins free, they are very nice and pretty to look at when the wine is young, but sooner rather than later, they will precipitate out of the wine. So the wine will lose color quickly. So a way the winemakers have to make that happen is to trap them into a colloidal formation by making them react with tannins, basically, with a bit of oxygen, which is what happened during aging in barrels. They also play a role in aroma modulation because the macromolecules are non-volatiles. Aromas, of course, are the volatile compounds, but the partitioning of aroma in the volatile space versus the solution depends also on the type and quantity of macromolecules. So a lot of the studies now are going to deal with, which are difficult studies, by the way, on how the composition of non-volatiles determines the flavor, the smell of the wine, basically, how much aromas are released or retained based on the colloids. Foam is another one. I know that in Sweden, beer is the main product, and there's a lot of studies of colloids in beer and foam stability of beer. Some of those studies, some 15 years ago, have been taken and transferred to wine, sparkling wines, namely. And that's a big role because proteins, polysaccharides have been seen to be tensioactive, so to keep the bubbles of a wine stable for longer, which is a positive attribute. So also the scope for studying colloids in this context. So as you can see, I mean, this is basically most of the research fields that I deal with, and a lot of people in enology deal with. So colloids are involved in a large section of wine science. At the moment, if I have to choose one for my research interest or for the feeling that the feedback that I get from winemakers is that clarity and stability are the main issues. Wineries and winemakers have problems in getting wine stable. So the wines, they bottle them, they're nice and clear, but then after a few months, they make a sediment and they get rejected by consumers or by the importers. And so it's a big money loss. And they don't know why. So there is a lot of work to be done in there. And I think AF4 can really play a role there. So going to this slice of the cake, the colloidal instabilities. So colloids in wine, they have many positive aspects, but they are very dangerous because they can grow, aggregate too big, and become unstable. And it depends on which wine we consider. White wines, the main issue is protein instability, so protein becoming unstable and aggregate over time. In reds, the situation is very complex and very unknown because red wine, they throw a precipitate. And if you look what's in there, you find that it's color, you find that it has polysaccharides, you find that it has proteins, but we don't really know until now what the mechanism is for this sedimentation. We only know that it's getting more and more frequent. And so it's getting more and more of a concern. I wonder if we should talk about this or not. Okay, but just to give a quick idea, in white wine, this is basically the protein haze formation general mechanism. We have your stable protein in solution. Somehow it unfolds, it aggregates once it's unfolded through hydrophobic attraction. There's a growth of aggregates, and then there's a cross-linking of other wine components that make a larger aggregate, which is visible as a turbidity. So when I was a PhD student, this was my scenario. We have to put names to those question marks. I didn't have the AF4, which would have helped. But so the approach was to purify the proteins, the polysaccharides, the phenolics of the wine, and to study them separately. So differential scanning calorimetry to see the melt temperature, crystallography to show the structure, the amylase scattering, tracking analysis, and so on, to try to understand, which we did. And now we have a very complex and comprehensive mechanism for protein haze formation in white wines, which is important because if we know the mechanism, we can find solutions to prevent it. Okay, so the idea was that. But without going into detail, proteins, they unfold, some of them refold because they're reversible, then they self-aggregate, and then they cross-link. Through the action also of phenolics, polysaccharides are involved in that. So there is, we know a lot about this mechanism, but AF4, I think, in this context could help us understand even better, especially the last part, so from the self-aggregation to the cross-linking of this. In red wine, as I said, the colloidal instability is more complicated because there are phenolics in there a lot, which are very reactive and they cause issues. As I was saying, this is becoming more and more of a problem, especially in changing climates, because macromolecules, they are linked to ripening. So the more the grapes are ripened and the more macromolecules we have, so the more likely we are to experience colloidal aggregations, precipitations. A lot of that is due to the reactivity of the phenolic compounds. Phenolic compounds, they're very reactive in the wine environment. They become even more reactive during aging through small oxidations. And so they can interact by themselves or with other macromolecules, proteins and polysaccharides. And they can form these colloids, which, as I was saying before, they can be stable or unstable. They also can interact with fining agents, so the additives that have been added. Daniel was talking about PPP or vegetal proteins, stuff like that. They can enter the system and mess up with it a little bit. So at the moment, until now, wine colloids, macromolecules have been studying with this fractionation, purification, reconstitution experiments. So try to simplify the system to understand what's happening. So a lot of electrophoresis, DLS, exclusion chromatography, tracking analysis, and so on. But most of these methods, they are complex, and they just give you partial information because you always have to break down the wine into individual components and then build it back up, which is, I mean, colloids, we know they're very unstable by nature. They're stabilized by hydrophobic and hydrophilic attraction, so weak interaction sometimes. And so by doing that, of course, you are not seeing the real colloids, you're seeing something else. So the results you get, they are maybe meaningful, maybe not so much. So this is where the relevance of this thesis and this technique comes in, because AF4 allows to separate and to look at colloids into native condition, which is something unprecedented in wine, which gave us the ability to study more, for example, the mechanism of colloidal formation in red wines. But I think I will skip that if you're okay, and we go just to the last part because we are see the minutes here, and it's best if we go to the relevance part. Okay. So the previous part was just to say that through AF4 we could start to understand how colloids are unstable in red wines, but there's a lot more to do, and some of that is in here. So for me, AF4 can solve a lot of the key scientific questions in wine science. For example, for me, it's going to be a key tool to elucidate the mechanisms leading to instabilities. So we can produce new information that can lead to new strategies to manage them, to prevent them. We can use it to study the interaction between wine molecules and other components, so the macromolecules, like with aroma, with the yeast and bacteria, fining agents, and so on. Something that has been partly done in the thesis, I don't know if it's in the second or the third paper, maybe. Monitoring winemaking process, something that was done in the last paper presented by Daniel, very interesting one. So to get information on what happened during different stages of winemaking, so that you can feed back this information to the producer to inform their decisions. It can also be used as a tool to differentiate wines. So like as a characterization, seeing if you can set the wines apart, maybe by origin, type of vinification, age, style, altitude, so on, by using the profiles of A4 without analytical techniques, without destructive methods. So with the first two of these suggestions, on-light detectors, they need to be coupled with experimental design. Okay, you can study wine, but you can make wine in a certain way and then study that. So controlling the experimental condition of winemaking can lead to wines with different composition that you characterize with an online system, and then you can try to understand, relate it back to the composition of the wine. The last two, especially the third, they need to be high throughput. So they need to be something which is done online, especially if you want to give feedback to producers while they're doing it. I mean, fermentation is a quick process. Of course, none of the systems that we have available right now are quick enough to give colloidal information. AF4 at the moment, at least from the results of Daniel, is not yet quick enough, but it has the potential to become quick enough, maybe in a simplified version. So if a winemaker would have a tool or easy version of AF4 that can tell him how their colloidal formation is forming over time, almost in real time, that could lead to quick decision, for example, to introduce oxygen to the fermentation or to, I don't know, do a clarification or something like that. So it has a great potential. So Daniel, or I was thinking about, okay, what can we use AF4 for in wine science? So I came up with a couple of slides full of questions. So there's a lot of ideas here, and there's a lot of experts in the technique in the room. So hopefully they're useful, but they can also be a starting point for our discussion, Daniel. So, for example, how are macromolecules interacted in wine to form the colloids? For me, this is the main application, maybe because it's close to my heart. But I think this is the key, the most valuable use that AF4 can have in the short term. How the macromolecules interact with other components to modulate characteristics like aromas. When especially are colloids formed, because colloids, we find them in wine, but at which stage of winemaking are they formed? Are they in the grapes? Are they in fermentation? And the last paper was really nice to see that, because he was looking at exactly this problem. So not the only one that thought about it. It's nice. What are the contributions of the different parts of the grapes? Because grapes are skin, seeds, pulp, stalks. So each of them with a different composition. So as the compounds are extracted into the wine, depending on the processing, the colloidal formation will change. How's the composition and the functionality of colloids going to change in wine? So it's not a static process by definition. Colloids, they change, they grow, they aggregate. So how's that going to modify? And this was also partly addressed in the fourth paper, where there was following up to 1 year almost from bottling, because wines is a product that is, most of them are made for aging. So we need to know where things are going, and hopefully in advance to predict. What are the impact of stuff that we use in winemaking, like fining agents and additives? How do they affect colloids? It was interesting to see, Daniel, in when you use, I think, bentonite or vegetable protein, there was the peak 3 was increasing in size in the malt signal, while the UV was decreasing. So it's interesting to see that you add a fining agent and then you get something which is removed and the size is increasing. So it's going to be interesting to see if this is going to affect the stability of that compound, for example. What is the impact of variables of winemaking, like oxygen, storage material, aging, and so on, for the stabilization of the color of red wine? Because this is another important problem, having a red wine which stays red for as long as possible and doesn't become orange or light color after 2 or 3 years. How can the vinification techniques be modified to make more stable or higher quality colloids, for example? Sorry, it's getting a bit boring with all these questions, but maybe I'll put them all there. And I was asked by Bjorn yesterday at dinner, so I came to the hotel and said, okay, let's think, how many things can one do? the role of many, but I don't want to bore you, and it's not about me presenting, about our discussion with Daniel. So, but just to say that they can be studied in the context of form of sparkling wine, or astringency, reaction with salivary protein, and the stability in the broader sense. Okay, so if I have to say a what do they call it, relevant statement, I think that this is really relevant. It's really at the forefront of the field. People in wine science, they are still not fully aware of this. I think it's still only a few papers, but I see more and more interest, and I'm sure that it will become more and more used in the future. So that's all I have. So thank you. Now.
Thank you for this enlightening review of the research field. Very interesting. And you started with the questions, so I think we should start now with the question section.
Should I stay here?
No, I think
go there. Okay.
you sit there.
It is okay for you to stay there. That's the best.
As you wish.
We need a mic from there.
Okay, so yeah, you decide.
Okay,
So
okay. I'll
should
take
we
here.
take down this?
Slightly, yes. Stop share.
Yeah. Yeah.
Okay.
You tell me if you need a break or something. Otherwise, we can continue the meeting. Yeah.
Okay. Do you hear me, Daniel?
Yes, I can hear you well. Do you hear me?
Okay. Okay. So I think now it's up to us to discuss. So let's discuss.
Yes. Great.
So let's start. One question that I already discussed with Bjorn yesterday. So macromolecules versus colloids. Okay. How do we call them? What is the difference? I don't get it.
Yeah, I think this is a good question, and maybe I forgot to mention that during my presentation.
No, you did, but I just want you to elaborate a little bit more.
Well, what I forgot to mention is that this classification we did was a little bit arbitrary, just because we wanted to differentiate one peak from the other. So, but we didn't mean that in the colloidal fraction polysaccharides can be included, or in the wine macromolecular fraction proteins and phenols also can be present, that we know that it is like that. But the thing is that we needed some kind of nomenclature, so to say, to differentiate these both populations. So we decided to call wine macromolecules to the polysaccharides and wine colloids to the condensed tannins or proteins. But of course, it's a mix, but in this mix, the proportions are majoritary for the wine macromolecules for polysaccharides, in the wine colloids for proteins or the condensed tannins. So that is the question or the answer.
Yeah, no, I understood reading because I was very confused at the beginning on this nomenclature, but then reading the thesis, I understood why this was done. I just wanted to to check with you. And maybe staying on this, how did you assess what's inside the wine colloids and the wine macromolecules? Because you say the wine macromolecules are polysaccharides, basically. What gives you the ability to say that? How was that checked?
Yes, I think we, in the second paper, we collect fractions.
Yeah. And
we just wanted to know what is in there. For instance, we collect from the Cabernet sample of the Argentina wine, I think 15 times fractions, and we concentrated, we inject in the HPLC. And there we see that we have some phenolic acids, some anthocyanins, but also we understood that these come from the hydrolysis of the tannins. It's not precisely these compounds which are detected that are part of the colloidal fraction, but we just wanted to show that there are phenolics in the colloidal fraction, and we did the same saccharide analysis or monosaccharide analysis in the macromolecular fraction. We found that the majority of the macromolecular fraction is in the polysaccharide. The majority of the polysaccharides is in the macromolecular fraction. So we did HPLC and anion exchange chromatography to both fractions.
Okay.
to
Okay.
detect.
So you
to
test
detect.
analytically then, and to be able to say that. Okay. And can you? I mean, I know why, but can you explain why you have to give it a name and a composition to these fractions? I mean, because you use that later on for the DRI experiment, I suppose.
Sorry. Can you tell me again the question?
So, for example, you were what is the Dndc ratio or the CDN? I never remember. You were then using or calculating a specific ratio for each of those families, right?
Yeah. The specific absorptivity, yes.
Yeah. Can I ask you how that idea came about, or what was the problem underlying that decided you to take this approach to solve the issue?
Yeah. I think it's a good question. And if I remember well, I think we had we needed to realize if this colloidal fraction is composed mostly for proteins or by macromolecules, or for proteins or for phenols. So we decided, or we said that, okay, if the specific absorptivity of a protein is around of 0.7, and the specific absorptivity, the molar absorptivity or specific absorptivity of phenolic is high, it should be higher, like 1 or 2. So we decided to calculate this value to say that in the wine colloids can be composed mostly by proteins or mostly by phenols. So and we found that some wines, this specific absorptivity is much higher than the others. And even in the red wines, we found that this ratio, this value of the specific absorptivity can be related with the aging of the wines or the phenolic content. So we said that, okay, the younger wines can be lower in the phenolic content, and more older wines can be in major proportion of this phenolic content can be present in the colloidal fraction, so thereby the specific absorptivity should be higher. So it was a parameter to see the ratio or the content of the phenolics or the proteins within the colloidal fraction.
Okay, and speaking again on this, I was interested also if you could tell me a little bit about how the dialysis process came about as an idea. Because I think it's a clever way of doing it. So if you recall, what was the genesis of this idea, and what was the issue that you were trying to solve with the dialysis?
That is related to the Dndc values, because if we want to determine the molecular weights and we need the Dndc for each fraction, and also the Dndc values are included in the determination of the concentration and the specific absorptivity of each fraction or population, but also it is different for each wine. So for quantification, we need the value of the refractive index increment. So to be able to determine that, first we needed to determine the increment, the refractive index of the total solids, of the wine. And then we use the refractive index increment of the wine macromolecular compounds of the from literature. So at the end, we were able to determine the refractive index increment of the colloidal fraction thanks to the dialysis. So it was a long process for do the quantification of each peak and each wine, because we realized that this value changes in the wine colloid fraction, but also in different wines. So we didn't have another option to. If we wanted to do a characterization that includes the concentration, we needed the value of the refractive index. So we decided to do this by dialysis first.
Mm-hmm. And so this value now can you keep it as a given. So if you do it again, this is a value that stays, or do you have to adjust it in if you change wines? I'm asking because I'm not very familiar with the FFF technique, so maybe it's a stupid question, but
No, I think it's a good question because the DNDC values, for instance, it's what I believe for the white wines that we have calculated during the clarification, they can be used for quantification. The other persons can need the DNDC value of the wine colors and they do run clarification. They can use these DNDC values and they do the quantification of the removal capacity of different clarifiers. But if you want to use the same DNDC values obtained by dialysis in the aging process, where new particles are forming, the concentration varies, you can't.
okay.
So it depends of the winemaking stage where you can maybe use as a reference or literature these obtained values.
Okay.
Because during the aging, it tends to change the concentration and new particles are formed. So while during the clarification process, it won't change too much if you use a reference, a DNDC value, let's say of 0.18, then therefore you have a molecular weight with this DNDC value of 25,000 grams per mole. But if you use a DNDC of 0.19 or 0.20, the molecular weight, it will not change too much.
Okay.
So it's okay.
Yeah.
Okay.
Yeah. So it's close enough, let's say, then a good approximation. Okay. Okay. So well, you talked about aging. So I had a general question. If you can comment about the role of aging in the formation of colloids.
So sorry, what is your question again?
During aging, you said the colloid change. Okay. So and you looked at that a little bit in the last paper about the change in aging. So well, let's maybe talk about that directly. It was very interesting to see this modification of the size. I mean, the magnitude of the colloids formed during different vinification stages. So it starts high, goes down, then goes back up. So can you maybe elaborate a little bit more on this?
Yes, I understand the question. I think that what I said is some properties changes during the winemaking. Most of the properties changes, but during the aging, it will depend on the grape variety, I think, because it depends on the profile of the wine that was aimed. Because during the aging, we know that we need to prevent the stability during the aging, but we use different techniques according to the grape variety or the kind of wine we want to achieve. So I think what I show is that maybe it was not clear, but some of the wines during the aging, they can be prone to have more polymerization if you have more phenolic content in the colloidal fraction, and others that perhaps Merlot, that it has a moderate tannic character. During the aging, the wine color formation or the particle formation of this colloidal fraction, it will not change that much during the aging as, for instance, for Tempranillo, that was really high in absorptivity from the beginning and during the stages of the winemaking. So during the aging, also it still has the potential to polymerize possibly. But of course, it will depend of the stability during the process that has been tried to achieve during the cold stabilization and all these stages. So if possibly, I mean, it depends on the winemaking process, what will occur in the aging, but also depends on the phenolic content, that if some grape varieties are tended to polymerize or be more tannic.
Yeah. So what do you think would have happened if you waited another year to check your wines in the last experiment? I know you didn't do it, so you cannot have but what would be your guess?
I mean, in the same question, we are following the same question, basically, right? So in the aging, we will have another 1 year for aging, right? That is your question.
Yeah. If you still, if you wait 1 year longer to analyze, do you think that the size will be bigger, smaller, the same?
Yeah, I think that will depend on the grain variety. And the wine, the grain variety will depend on the grain variety and the profile of the wine and the character of the wine. But it looks like the absorptivity of the Tempranillo wine and the Garnacha, that they had more concentration in the beginning of the phenol content in the macromolecular fraction, will still increasing. While the others, they will move around a bit, but yeah, I don't know how much to expect the change, but what we show with the papers, it was possible to predict that in some grape varieties and some samples, the polymerization can follow and can continue, but in others, no. So I think the A4 is useful also to predict the aging process depending on the grape variety.
I think so too. I agree. I would hope you do this analysis 1 year later to see what happens. It's a very interesting topic, very relevant for the stability of red wine. So that's why I was asking, because I always want to see more data. Something in mind, but now I forgot. Maybe one more general question. I know we jump back and forward a bit. Did you have to adapt your method from analyzing whites and reds, or was it the same? The method for the AF4, is it exactly the same for analyzing white wines and red wines, or do you have to do some special modification?
Yeah, good question. I think it is slightly modified, but for the injection volume of the samples, but the cross flow, the flow of the channel, all these things are similar. Only the injection volume was different because in the white wines, we needed to inject more after the clarification, and for the clarification to get a representative intensity of the peaks. But with the red wines, and I think that depends also on the particle formation and the content of the polysaccharide. You can inject not too much, 40 microliters. I mean, in the last paper of the vinification, we inject 40 microliters. In the white wines, we injected 400 microliters. And in the first paper of the Argentina wine, we injected 100 microliters. And then we tested the methodology for avoid overloading and to be able to separate properly the resolution of the peaks and consider also the void peak and the elution after the cross flow is turned to zero. So we optimize all these parameters of separation with the injection volume, but then the rest was the same.
Okay. So basically this. Oh, another thing, they use a membrane. They use a 510 kilodalton membrane to
Good question. I forgot to mention that. Yes, we try to use 5 kilodalton, and we also use regenerate cellulose and polysulfonate material. But at the end, we get good results only with the membrane of 10 kilodaltons of generate cellulose. But we had some interactions with the membrane, and some color were remaining when we used the polysulfonate membrane. And during that time, when we wanted to purchase 5 kilodalton membranes, we had some troubles and they were not providing. And the ones that were provided and we used, they were not working. So we decided to use the 10 kilodalton membranes.
Okay. So all the samples or the analysis are done with the focusing step of the. Is that why the retention time changes from the first paper to the other one, maybe?
Yeah, I think that's related in the white wine paper that we started the elution, I think, for 20 minutes. And this changes because we needed, as we injected 400 microliters,
okay,
we need time to inject the sample and to do the focusing
Okay,
And we
okay.
need like a 10 minutes extra. But
I-
for the other thing, we injected less. The ball peak and the retention time is lower. It's
I see.
shorter. I should say.
Okay, okay. On the third paper, you decided to study clarification effect in wine. Why did you start from this as a first application of AF4 in wine? It's a curiosity. Yeah?
Well, this was a discussion with one of my co-authors in Spain.
Mhm.
So we have different plans, but at the time we had this process or this project ongoing. So it was a parallel study of the clarification and to evaluate if there are some contaminants of soil contaminants, so they can affect. Don't remember well really the other project, but we had these samples available at that time. And then we were thinking about other projects, but we took this one first, just because the availability of the samples, I would say.
Okay, okay. And do you remember how you decided the clarifiers to use and the addition rates? Because so it was to remove impurities, basically. You said so. It was to try.
You mean with the doses we have used? How we decided?
Yeah, yeah. Why did you choose certain doses? Was it as a result of a trial, or was it like manufacturer suggestion, range, stuff like that?
I guess it was just a common procedure that they used there in Spain.
Take a second, I need time to find my other question. Am I supposed to do it all? You cannot say, "Oh, can you ask a question while I look for the next one?" Or
There is no problem. You can do it as you
oh,
want.
because I don't want to keep you waiting. But give me a
No
second,
problem, no problem.
because I kind of lost track of where I was. This paper, there was something I want to ask about the UV decrease. I don't remember what it was, but there was you showed also in your presentation today, there was a correspondence of the molecular weight of proteins in red wines, or proteins of colloids in red wines. You had like something around 2027, something about 70, and something 160. It was one of your slides of today. I don't remember now which paper it was, but you found that with AF4, you found 3 populations with 3 different molecular weights. Okay. And I think it was in red wines. I'm pretty sure it was, which is an interesting observation because in our studies in red wine, we never find 3 proteins, which would be the material 25, 26, 27 molecular weight that you found. So the question is, you understand what I'm discussing, what I'm talking about?
I think maybe you are confusing a bit because I just provide a table for molecular weight for the second paper, and there we have 2 populations only.
Okay, yeah, you have one at 20 something, one at 60, 70, if I remember correctly.
Oh yeah, you mean only, you refer only to the value of the molecular weight, not the number of the bits.
No, the value. You had the nanometer, and then you show the molecular weight of the populations. I think you had the 3.
I can share if you want.
If you want, maybe yes, because I'm getting a bit lost. Can you?
I don't know if you are looking at it now. Sorry, I will share.
You want to share so also the people here understand what we're talking about?
Yes.
Okay.
Are you watching it now?
Yeah, I see it. So you had here, let me see, the P1 like 22, 25, 44, 24. Okay. So this is a molecular weight consistent with the free pathogenesis related proteins. It is the P1 molar mass molecular weight.
Yes, yeah, I think this is one color fraction, but this is for the red ones. We didn't provide the values in this presentation for the white ones, but if you refer to the white ones, we can go to the paper.
No, I meant exactly this one because it is, I mean, it is a comment more than a question. Is it interesting that you found these molecular weights? So this means that there are some free proteins in those red wines because this is the size of free proteins, which very rarely we found in free form in red wines because most of the proteins are normally interacting with phenolics to form and polysaccharides to form a colloidal molecule. So it was interesting that you had this P1, P2 consistent with the free form and the aggregated or form of molecules. The question was, have you got a gel about this, an SDS page that you've done that you haven't published anywhere?
Okay, I'll have to clarify something. This population wine that we said that is the wine colloidal fraction.
Yep.
We assume that in these red wines, there are because of the DNC values we found in this set of samples of the red wines or from high altitudes, these are not really proteins, are mostly condensed tannins from 25. I mean, it could be that there are some proteins and polysaccharides attached to these colloidal aggregates or particles, but it's based on the phenolic content of the colloids. But we did what you say of the gel electrophoresis in the white wine paper, and we correlate with the electrophoresis the protein values, but in this, the protein values of the molecular weight, but in this paper of the white ones, where we correlate these proteins values with the gel electrophoresis, we assume that there are not that.
Okay, so
they are not more philos and they are more soluble because it's a white wine.
Okay.
So here we said that this is colloidal fraction is not from proteins because the Dndc values of this set of wines are rather high, which tell us that it's more composed by phenolics than proteins, but it would be proteins, the Dndc values will be lower. So we can show the next.
No, I understand where you.
Here we have the Dndc values in only for markup. We could say that this population is rather dominated by proteins.
Okay.
But not the others, because we know also that these are high altitude red wines and the tannic character is high of these red wines. So therefore, and the Dndc value is high. So therefore, the wine colloid fraction is composed mostly by polyphenols than proteins, which gives the absorptivity values, where the absorptivity values here shown that they are above 1. So we can observe here something strange, but has its explanation, that we observe the specific absorptivity for the colloid fraction 0.8, that is the lowest, and the Dndc value here for this is quite high, but only this is because this fraction, this colloidal fraction has no peak, and it was very low in concentration. So this therefore gives a very uncertainty in the measurements of this value because it did not have a peak to quantify. So the concentration was low and the errors of the measurements were high at the end in the DMC. But if we consider the other values, the absorptivity, specific absorptivity for population 1 of the wine colloid fraction is 7.157.6, much more than 0.7 what we expect for a protein. So therefore, this is not a value only for proteins.
Okay. I got confused because I not being familiar with this value that you calculate specifically for this. I thought, okay, that's a molecular weight consistent with that of free protein, like the one that you showed in the gel in the white wines. But so this for you, it's polymeric tannins, small polymeric tannins. Okay, okay, that's an interesting.
Because we did also the analysis of the HPLC, and we showed that there are at 280 and 350 and 530 nanometers, I believe we found anthocyanins, and we found flavonols in phenolic acid. So in this colloidal fraction, there are polyphenols, which are part of this molecular weight, of course.
And okay, I found a question which is we partly discussed already, but so in a paper you found 2 populations, then you found 3. I know it's difficult to explain, but have you got any idea of this? Why do you find 3 populations in one and not 2 as the first one?
Yes, I have to say that.
Okay.
It's I want to show my fractograms. Yes, here. So you mean in the red wines, we found 2 populations and you found 3. But also we found in the 4th paper, that is red wines, in the vinification study, 3 populations as well in the red wines. So we asked this, and we were wondering about this. And what we can believe, or I think could be a reasonable explanation, is that in the vinification study, we noticed that the second population, depending on the grape variety, has intermediate properties, but some of them high absorptivity, the second population, that we could say, okay, this is formed by polyphenols or by proteins. And the others, the second population, were more polysaccharides because of the high absorptivity. So we needed the high absorptivity and the density to classify the nature of the population. So what I want to say with this is that it's possible that during the aging, one of these intermediate populations can be part of the first population or the third population. And then according to their properties, they merge with 2 years. And these wines that shows only 2 populations and were really rich in phenolic content, and they were more mature. They were more mature, and the aging was different than the ones we showed in the 4th paper, where they were maybe 6 months aged, and with a so maybe this comes back where you ask what will happen during the aging if we give 2 or 3 years to these samples. Possibly one of these peaks can merge to the other, because this shows that it's changing a bit in some properties, and we could say also that in some properties were stable during the vinification, but in the aging, other things, of course. And I mean, it could be related with the aging and with the.
I think it's
how mature or younger is the wine. So I think these wines were very mature, and we observed 2 clear different populations with 2 clear different properties between populations. But in the Spanish vinification of the red wines, we have 3 populations, but with intermediate values, the middle population, but the age was 6 months.
Yeah.
So,
I think it's a very likely explanation that either something drops out or grows or becomes part of another population. And yeah, those wines were quite a few years old when you analyze them. So that could be something also to look in the future, effect of aging to the distribution of this population, because obviously they seem to become simpler in a way. There's a loss of one, which is
yeah, I don't believe we can get a wine with 4 populations, but I think 2 or 3 would be
hopefully not, because then how do you explain that?
Yes.
Okay. Okay, so I jumped from here and there because I got a bit of notes, got a bit confused. But in your thesis, you showed a picture of the dialysis. It's page 21, if you want.
Yeah, I have it.
Okay. So, and you made a comment. You say that there were difference in solubility of polyphenolic compounds because some color was released more than in some sample than other. Did you ask yourself why, or did you give yourself a possible explanation of what this difference?
Yeah, I mean, it is clear that the wine's colloidal fraction has different phenolic content, different rates of the phenolic content. And so in some wines, there are more soluble polyphenols. In other wines, no. So in other wines that, for instance, we are watching now a Cabernet Sauvignon sample in the presentation, and it shows high absorptivity, which telling us that it has a high content of phenolic content, while in Malbec Quintanat, in the retained fraction of the wine colors, the absorptivity is much lower, saying that, okay, the solubility of these phenols were higher and they were dragged through the membrane. So this picture reflects the differences in the content of the wine colors and in the phenolic content of the wine colors regarding their solubility.
Okay. Did you, when you analyze red wines in the second and fourth study, you didn't have a detector for 520 absorbance, right? I mean, did you follow the color? Did you see where the color was coming from? Was coming out in which fraction?
Yeah, I understand what you mean. You mean in the UV signal? Yeah, it was set to 280 only. Yes, you're right. We didn't follow 530. That could be really helpful because we can track maybe in the fractogram where the color is going or the proportion of the color.
Yeah, because okay.
I think that's a good idea and good point to do it. Yes.
Okay, just a curiosity if you notice the color for. Okay, I stumbled on paper one. I had a question here. Why was the focus on phenolics on the first paper?
In the first paper, okay.
Yeah, the one on the altitude Bolivian wines, because you show a lot of phenolic result, and I was wondering if there was a reason for focus. I mean, you gave a reason about the altitude having more UVs, and so phenolics are important.
I think the intention was to first see, just to provide in the beginning a full characterization of phenolic content of South American wines. But what we wanted to use later is some of this wine for FFF analysis. And we thought at that moment that if the phenolic content is higher in the wines, thereby the wine colors and the particle formation in the phenolic fraction will be higher. So we intended to do that and to collect a rich variety of wines that shows high phenolic content, and then use those for the FFF analysis. That later showed that it's partially true, because as you say, there can be particle formation and we can detect colloids, but some of them can be very soluble as well. And we can have a really rich wine in total phenols, but the majority of these phenols can be soluble. So, but it was the intention in the beginning.
Okay. Good. Almost running out of questions. I don't know how long I have, but
Oh, lo están viendo. Perdón.
Ah, okay. Okay. Yeah, I didn't recognize myself. Good. Okay, I'm back. So, paper number 4. I think it's page 20. You, just under the table 6.
And which page, sorry?
20
2020.
of the paper, so on the paper sections.
Okay.
So just under the table, there's a sentence where you say about during the aging period in stage 5, which is the after bottling, the absorptivity remarkably increase again, which is what we discussed before. So you made a comment here that they say that this increase could be due to the release of new compounds. And I was wondering what you meant by this.
No, during the aging period in stage 5, the absorptivity remarkably increased again in the populations, indicating new properties and or the formation of new types of particles.
Yeah, now the following sentence, you said that the evolution and release of new compounds. I was puzzled by the release of new compounds. Like,
okay.
where do they come from, or what you meant by that? Because I didn't know that.
I mean, I can relate a little bit to perhaps a restructuration of the tiny particles during the aging, or the formation of new particles during the aging. So I think these particles can have are composed by phenolics, so they specific absorptivity can increase again during the aging. So I try to refer to that.
Okay. So you think, it's more the formation new part, because I read to me like a release from somewhere, and I didn't know where,
I think
where
they
would come from.
It shouldn't be released. You're right. But this is not published yet. So
I know.
Thank you very much for noticing that.
I don't know if it's somewhere, but you don't talk a lot about monoproteins in the thesis. A couple of times, yes. And monoproteins are quite important in colloids in wine. So I wonder if you have, I don't know, if you want to comment on the role of monoproteins in colloidal formation of wine. So if you have some ideas. You say, I mean, actually, in this paper, the previous page, you said that possibly monoproteins might be part of the population tree.
Yes. Well, we didn't focus in the monoproteins because we didn't have analysis for evaluating monoprotein content. But I know that they have a lot of properties during the winemaking. They can stabilize the color. They can stabilize they can work as a protective colloids to avoid some kind of reactions or polymerization. And I don't know, I think they are used also during the stage 4 with the colloid stabilization. Possibly they can use for colloid stabilization. Or of course, can other compounds be used? But I mean, I know that there are a lot of benefits of the macromolecules, but of the monoproteins. And then we did the analysis in the paper 2 of the polysaccharides, and we said that possibly these monosaccharides are coming from the mannose content, are coming from the monoproteins. But I mean, all these techniques with the monoproteins are related to the winemaking process, and at the end we didn't do any wine, and we don't have access to the winemaking process to maybe play with the monoproteins and things like that. So this is why it was a little bit aside from our studies.
Okay. Yeah, I think at one point you analyze sugars and there was mannose there. So I think on the second paper.
Yes, in the second paper.
Yeah.
Yes.
Yeah, no, because they are. And do you think that monoprotein will have the same Dndc as a polysaccharide, or?
That's a very good question. I could say about this that in the literature, the value use of the Dndc, I think for polysaccharides is around 0.146. And we use 0.14 because of the alcohol content. So we recalculate this value to 0.14, but this is a general value. So I know the monoproteins show a little bit of proteins, but has a little bit of proteins or UV active groups, but I think can be a higher value, but very difficult to say or to quantify or separate.
But as you said before, it wouldn't change much the outcome, because if it's 0.14 or 0.15 or 13,
at least in the macromolecular fraction, we didn't focus too much the changes, and we didn't monitor. But it's a good question, maybe how to calculate the Dndc only for monoprotein. But it's an answer that I don't have.
Yeah, no, it's fine. I think no one does.
Yeah, because the monoprotein is just within the macromolecular fraction where we have another polysaccharide.
Yeah.
And the monoprotein is not the majority part of the macromolecular fraction. Perhaps it's the second.
Okay, if you go to page 64, which is the last page of the basically of the conclusion section, half the way you start with a paragraph which undoubtedly this approach can lead to a multifactorial problem. I was wondering if you could guide me through this little paragraph a little bit, elaborate a bit the thinking behind this.
Let me read it, please, because I don't remember it.
Of course, I'm reading as well. Especially the part of evaluating the yeast and bacteria. I wonder what approach you would use to do that.
Okay. I think in the beginning I said a multifactorial problem because there is a lot of properties that are changing during the winemaking. And if we have, as we have here, different grape varieties, so we cannot explain all of that in one single plot as I try. But then I said that, okay, if we use different type of yeast and bacterial fermentations, possibly we can have a different macromolecular and colloidal peaks. So, and therefore there we can maybe, well, I don't know really what will happen if we use another enzymes and how it will look in the fractograms and how will be the end of the quality or the perception of the wine. But my idea is that trying to knowing that knowledge and using that to modify and try to achieve a special wine, knowing these parameters in the middle of the vinification, it can be very useful. But if you ask me what will happen if we change yeast strains, what will be the outcome of that, I don't know.
We don't have the crystal ball, but no, it is. I also think that this technique can be useful also, to check the microbiological aspects of wine. Yeah. I think that if you want, I can be more than happy with my questions. And okay?
Yes.
Okay. Daniel, thank you very much. It was a pleasure talking to you.
Thank you, Matteo, for your nice questions and for give
unfortunately
a way to explain everything.
unfortunately
give a
for
good
you,
way.
it's not finished. So
No, it's not finished.
stay tuned.
No, of course. Thank you very
Bye,
much.
Matteo. Thanks a lot.
I think I'll see you later, but bye.
Thank you for these interesting discussions that you have had during the time. So now it's the time for the examination committee to ask their questions. And I hope I can invite you to come here to give your questions. And if you, Professor Yanis, want to start with your questions, that should be okay.
Yes,
Yeah.
the committee accepts.
Yeah, yes.
I'm not aware.
I will give the floor to them as well. Yes.
Okay. Thank you for a very nice discussion.
Hi, Daniel. Do you hear me?
Yes.
Okay.
Hello, Chronicles. It's a pleasure to know you.
Yes, it's a pleasure also to read your thesis, and I will start to congratulate you because
Thank you
it's
very
a
much.
very interesting work and very complicated. I'm not a wine expert, but I can understand that you had a lot of different issues to think about this thesis, both in the colloidal issues and also analytical issues. So I think also I listened your discussion with Matteo, and I think you have more or less a lot of ideas and a lot of you think a lot what's happening in all of this topic. So my questions are not so much. The first issue that I would like to ask you is you mentioned that you use a liquid carrier in your analysis at pH 3.6. Do you remember? And then you use ethanol. And why do you choose this pH? And also if that has any effect on the whole analysis of your different compounds.
Yes. Well, there are some reasons. I think one is to mimic what is occurring in the same condition that is occurring in the wine. So the wine is pH 3 to 3.5, 3.6. Maybe there are some wines that have more extreme values, but also the ionic strength and was the same in the carrier model. So we tried to simulate what was occurring in the wine when we do the separation, because if we run the separation in different conditions, possible some aggregation can occur if we not use alcohol at all, or for instance, if we use 50% of alcohol or too much ionic strength, this can change the interactions and we can generate aggregations. So then our detection or separation would be mislead because of the carrier model, and this is reacting with the sample. So we simulate the wine conditions in the carrier model to just separate and avoid, let's say, possible aggregations and things like that.
Okay. I'm not an analytic expert, so that's why it's. I'm not saying that there's anything issues there, but do you have any issues with the solubility? Because some compounds are more soluble and some others are not, and in that way, something is not detecting.
Yes, but it's similar what is occurring in the wines. If the wine is 3.6, we are running in 3.6. So what will be soluble in the wine will be soluble during the running.
Okay.
Once I could say that once I just tried to run the FFF with water, and in the red wines, I didn't see too much difference, but in the white wines, I saw that one peak decreases considerably. And I think this is because of the solubility of the compounds in water and in alcohol.
Yes.
This is why we wanted to simulate the wine conditions in the carrier model.
Okay, good that you validate this. Just I want to understand a little more. Very nice. Okay, and the next thought that I have about all of this, because you talk about colloids and macromolecules. So, do you have measure the charges of all of these materials, or the zeta potential, or how you call it, at different conditions? Because that will. You mentioned at your thesis that there are different interactions and so on. So, do you have any idea?
No, we didn't focus in this kind of interactions at all. But I think for aim, it wasn't too necessary to see the zeta potential in this kind of interaction because we would just wanted to fractionate and characterize these fractions and then relate this fraction with
Daniel, do you hear me? It's frozen.
Okay, so perhaps he has to shut down and start again. Oh, but he realizes, so. And now he's starting again. Just
Yes,
a
yes.
moment.
No problem. No problem.
I think it-
Hi, Daniel.
We are back. Some
Yeah, we are
technical.
back. That's
I was-
nice.
I scared, but I think it's okay.
Yes, yes, yes. I will not disturb you so much. So,
No problem. I think the Zoom it stopped working, but now it's okay.
okay. Okay. Yes, yes, because you mentioned in your thesis that you say, I think in the paper 3, that positively charged proteins may absorb that negatively charged finding material. So there are charges and they interact with different compounds. So that it would be very interesting, I mean, because all of these colloids.
Yeah, I think in the clarification process, when, for instance, we use bentonite, it will be very possible to measure all these zeta potential interactions.
Yeah.
I think there are some. I read some papers that they measure this with dynamic light scattering and the use of bentonite in the clarification, and they provide that info.
Okay, okay, but interesting anyway. And also, I mean, for example, the PVPB, the polyphenolic, I mean, is a negative charge, for example. So, and at this pH that you are using it. So in that way, that's useful to see what's happening in the finding process.
Yeah, the idea is to precipitate the proteins. As the proteins are positive charges at that pH in the wines, not all, but many of the thinning agents should be negative charges, but they can have different sources that can be polysaccharides or can be clays or can be synthetic polymers. But the principle is the same, that they attach electrostatically and they become less soluble and they precipitate.
Yes, yes, that's what I'm saying. Also, that is good if you could know a little more about the charges, but it's fine because also use the potato protein as a binding material, and depending what pH you are using, you have different properties on the binding in that way, or the pea protein.
Very interesting.
Yes, and did you see any swelling when you have this binding, or when you have your molecules, colloids or macromolecules that they bind to the finding material? Did you see any swelling? Because, for example, the PVVP, it swells a lot. Have you? That's, you have also the different sentiment, but also it absorbs water.
Well, I had the opportunity just to watch the wines before clarification and after clarification, but the sediments, I did not see them because it happened in Spain. So they proceed with the clarification experiment. So they send the sample after clarification.
Okay, that's interesting.
That was done by my co-author in Spain.
Okay, but did they use the same time when there is this binding and finding process? Because it's a time processing also, or is different? Just a curiosity.
You mean during the clarification process, if each clarified agent was treated similar?
Yes.
I am not sure.
Okay, Daniel, no problem. Okay, Okay, but it's very nice anyway that that you have looked all of these issues and okay. Yes, it's also for my interest about these interactions, these polysaccharides, wine colloids with salivary proteins. Is it a lot of work that has been done there?
I
And
think
what
there
kind
are,
of proteins? You talk about salivary proteins. What kind of proteins are? Sorry.
well, I think there are groups that evaluate this, the astringency phenomena, but we didn't make any kind of sensory analysis to see how bitter is the wine or how astringent or how pungent. So I didn't go into this really into the salivary proteins and the interaction that occurs in the mouth. So
Yes.
we just focus in the sample and in chemical analysis of the
Yes.
fractions.
Yes.
But I cannot tell too much about the interactions of the tannins with salivary proteins because I think this is a little bit other field.
Exactly. Yes. Yes. Just a
Can be
curiosity. It's a curiosity. It's not anything. As I was working a lot with some salivary proteins and so on. That's what I mean. Okay.
Yeah, I read about a little bit, but I'm not very aware now in connection with my results.
Okay, I don't have any more questions. I would like to congratulate you again for those very nice results and all of these efforts to clarify these different properties during the wine making and also the analysis. So thank you again and all the best.
Thank you very much, Chronicles.
Thank you so much, Yanis. Can I ask Professor Anastrom to... Sorry for this inconvenience. So, Anastrom, please.
Hello, Daniel. So
Hello, Anna. Nice to meet you.
the same. I have some questions. I would like to continue a little bit on Yannis' questions on the choice of the different clarifiers. Can we call them like that? So why did you choose bentonite? I think it was potato protein, right? And also the PVPP.
Yes. Well, I don't have a real clear answer for that, but of course the intention was to compare to evaluate if the FFF can see differences after the clarification process by using different clarifiers. So we use bentonite because bentonite is the most common, and we know that it's very strong, and it has its potential drawbacks, contaminations, and other things that removes aroma. And then we use the PVPP because normally also has been used, and we use the protein clarifiers as an alternative. But I know that there are plenty of other thinning and clarifiers or agents. So we focus in what we have at that moment and what we could do it. And this experiment was done in Spain by a laboratory in Vitec. So, and this was part also of another study where we took the samples. So I don't have a precise answer why we choose bentonite and maybe not zirconium, for instance, that they are the same kind of nature. But
I was thinking whether you were choosing them maybe because they have different kinds of natures. So whether they could interact with your colloids, macromolecules in different ways. It looks like they did to some extent, right? As you.
Yes. Of course, if that was the question was in that way, I think that just we wanted to see what are the difference and the impacts. And if we can see that in the fractograms in the FFF. And I think it was very interesting results because we could even see that we noticed different results even when different doses of the clarifier are used. When we use too much clarifiers, we are wasting money, time, many things. So we can use the FFF to evaluate how much of the clarifier can be needed, and this can be very useful as well.
I will go back and forward a little bit in my questions. I apologize for that. But Björn wanted me also, I think, to have some sort of an industrial view of this. And my question to you is, do you think that the need of defining the NDC, would that be a showstopper for this technique on a larger scale? How do you think around that?
You mean the calculation of the DNDC?
Yeah, to me it looks like it's not completely straightforward. It's a little bit complicated to define the NDC, especially you discussed with Matteo for the red wines. How do you see that for the future? Could that be a possible problem, or could one solve that somehow for use on an industrial scale or smaller users?
I understand what you mean. So we have challenges in the determination of the DNDC, which makes the procedure a little bit long if you want to analyze, let's say, 200 samples. So this is why we are using the online detection. You want to have faster analysis, but the DNDC is a drawback. And I think we methods to industrial level now, because it is very time consuming if you want to analyze 100 samples. So I think what we have to do is find another way to overcome this problem. And I think there are some possibilities, but not yet. So we are not at that level to apply this methodology directly to an industrial scale.
Thank you. So faster analysis of the definition, faster characterization of the NDC is needed. Is that your conclusion? And if that would be obtained, then possibly one could use AF for.
Yes, I think this can be used for research now.
Yeah.
Not for industrial, with industrial benefits yet, but it could be, it just needs a little bit more time of study and more insights about this issue.
Another thing, I think also what you are reporting in paper 4 is very interesting, and you can nicely see differences between the different stages and changes of what you call the colloidal and macromolecular fraction. But from what I understand, you have sort of a circle. It goes from larger particles to smaller and back to larger particles. In a way, I have two questions there. Do you know what's happening? But I also have a question. You can choose, because time is running, which one you want to take. How much are these changes related to the different process units, and how much is it related to the different grapes that you're using?
Yeah. So I think the changes of in some properties, for instance, in the size, could be that there is a clarification process, or there is a removal stage where we just remove a lot. And we have the changes in the absorptivity during the winemaking process, but for some grape varieties they were potential more richer in polyphenols. So when you have one stage that removes everything, these grape varieties that potentially were richer in polyphenols tend to increase again. But the concentration during the whole process was slightly not changing too much. So there are some properties that tends this dynamic cycle, other properties that tends and shows that can continue increasing, and others that kind of remain the same. as the concentration, not the size of other properties as the UV absorptivity. And when you talk about the ratio between the gray variety and the operation units used during the winemaking process, that might depend basically of the gray variety, but it will be difficult to give a number about the ratio of how this is affected, but there are tendencies from the gray varieties, that's how they were stabilized for the aging and how kind of wine you want to achieve, what kind of profile or character wine you want to have. And this follows a tendency, even the winemaking stages can be harsh, but also the winemaking has this strong impact in all the grape varieties. So it's a bit relative to that ratio, difficult to answer.
Yeah, I fully understand. Thank you so much, Daniel, for answering to my questions.
To you, Anna.
Okay, then we continue with Mats Lehmann. Yes, please.
Hello, Daniel.
Hello, Matt. Nice to meet you.
Good to meet you. Thank you for nice thesis. It was very interesting to read it.
I'm glad you like it. I read your thesis as well.
Just very short questions. So when I read the papers, the paper 2, 3, and 4, you have a slightly different injection, relaxation, and focusing time. And could you elaborate a little bit on why you choose different times?
Well, this was just to optimize the methodology of separation.
Yep.
So when we injected more volume in the white wines, we injected 10 times, I think, more than the fourth paper. So we inject 400 in comparison to 40 microliters. There we had to have more focusing time and more time to inject the sample and more time for the focus. And yeah, basically that, because otherwise if we would have injected 400 and had only 5 minutes for focusing and injection, we would have lost sample in the loop of the injector.
Yep, it's excellent. I mean, not everybody thinks about that, so yeah. And just a final more outlook. Now you have used 3 detectors online and then offline detection. And if you could choose one detector more, online or offline, what would you choose, and what would it give? What kind of information?
Well, if I, for instance, add a fluorescence detector that is available, because that is a big issue what we have.
Yeah.
So,
now you can choose. You can choose whatever.
I would, of course, be able to determine the concentration of proteins. That it will be very helpful. But I mean, depends of the aim of what we want to achieve, what we will need. So depends of the study and what we are doing in the winemaking process and what kind of the detector we will have. But I know that we are lacking in the online detections for quantification, for a more precise characterization, I would say. And I don't know. I don't know. I just perhaps had first fluorescence detector to follow the proteins and to determine the concentration of the proteins. That was something that we did offline. But later is something that is, I have to think a lot to answer that question more properly.
Well, thank you. It's a nice thesis.
Thank you to you. Thanks a lot for your work.
Thank you, Mats. Anne? Nej, but Sophie, you have something. Anne? So one more, Daniel, but not so complicated one.
Very welcome, very welcome.
Hello, Daniel. Thank you. It was a pleasure to read, even if I must admit that I don't understand so much of this, because I'm in a totally different area. But what I understand is that you measure a lot of different things, different properties in that may be important for the quality of the wine, the finished product. And that was what I was most concerned about. I couldn't realize how all these properties that you measure can have an effect of the quality and how it can help in the winemaking process. But listen to you today and also listen to the opponent that clarify to me a lot. So now I understand more. But if I can have just two small questions anyway, that you describe a lot of steps in the winemaking process. And in each step, the purpose is to measure the properties of the wine after each step. Then you got a lot of data, and that's, I mean, important to know what has happened in each step. But how can you do anything about it when that step is already finishing out? That is already, is that the information that you collect something you can use for the next step in the winemaking process? How I have a little bit difficult to understand how in each step actually you can go back. You can't go back and make changes what already has been performed. How it can be used in practice?
Yes.
It was not a small question, but you can just give some example.
Yeah. Well,
one example.
No problem. I think well, it can be tricky because I'm not a winemaker, but we didn't modify nothing. We just evaluate because this process was ongoing, and this process was ongoing to achieve some wines that they already defined which character, which kind of wines they wanted to have. And they were for sensory analysis. So were they designed in a special way? So we took the measurements of each stage and we tried to validate the FFF methodology we did in the previous papers to see if it would be useful. And we provide that it's possible to get information in each stage of the vinification, and these properties can be related to the quality of the wine. Let's say if the quality of the wine is relating to the aging or to the stability during the aging. And there in some of these stages, we could say that, okay, these two wines are potentially unstable or more unstable, or potentially they can polymerize during the aging, and they will affect the sensory properties, as will be more astringent or will be less astringency because in the process, some properties are precipitating or are solubilizing. And yes.
And then the winemakers will change some. Yeah,
yes, they make some modifications, but I think we are not at that level because we are validating now this methodology. But if someone has, as Matteo said, the FFF there in the where you produce the wine, maybe you can start to alter the process. But this will depend on what kind of wine you want to achieve. Yeah,
I understand. So just one small question. I really understand that this is very interesting for scientists. But what do you think the winemaker are interesting in this method?
Not sure. I think we show some potentialities. Matteo also. I think Matteo showed more, and I discussed a little bit this in my outlook future in the thesis, a bit in my dissertation. And I think that depends also on the skills of the enologist, how he can use this machine. But I think that the results are important for science, are important for the winemakers, and also are important for the people that is in the FFF field, because it's a new application and for the instrument. So I think what we need now is that just collect more data and run more wines and have more ideas to then all together the groups create a solid theory and then wait a little bit to settle and then use that to an industrial level.
Okay. Okay, good answer and congratulations.
Thank you very much. Nice to see you.
So, thank you very much from the examination committee and all the questions. Now, sorry. Now it's the audience. Do we have any question in the audience here in Lund? Any questions from you? If not, then I ask Jose Bravo, do you have any questions from the audience in La Paz?
Yes, if anyone want to make a question to the candidate?
Yes.
Dr. Monica.
Okay, we have one question.
Very nice.
Okay.
Yes.
Thank you. Hello, and good afternoon there. I just want to ask to Daniel if he can highlight something related with these parameters that he calculated related with the high altitude for grapes.
Yeah. So, okay. I think a parameter that is related with the phenolic content is the specific absorptivity. And with this property, we can assess how much phenolic content is in the colloidal fraction. So I think that is a very important property, maybe together with the apparent density, because if we have a fraction that is more dense and more compact and is richer in polyphenols, they will be classified as a one color. So, and we run different wines from high altitudes and from low altitudes, and we use this parameter. We can categorize them thanks to the online detection and to the equation that we have deduced from the fractograms in the intensity of the signals.
Thank you. Thank you very much.
Okay. Any more questions from La Paz? No?
No, no more questions. They say no.
Then, okay. Then I wonder if there are any questions from the people online in Sweden, or
Something in the chat.
there is something in the chat, but I,
You don't see it.
yeah, here. The task is open for questions, yes. So do we have any more questions from the people online? No. It doesn't seem so. So in that case, I close this defense. And now the examination board will meet together with the opponent and also the supervisors. And the supervisor and the chairman also from La Paz will participate online. we will meet in another room here. And I hope that the audience here and also in La Paz, that you will stay and enjoy each other during the time. So you will also know the response from the committee in a while. Thank you.
Okay, we will wait here.
We had a discussion, the committee, the opponent, and your supervisors. And we are really impressed by the performance you did today, the way and with the maturity that you responded to the different questions posed by Matteo and by us in the committee. So we are really happy to congratulate you as with the title as a PhD. So you passed. So cheers and congratulations.
Thank you.
You're welcome to the Big Bang Theory community.
Yes, that is. Mauricio.
Yes.
Plead if you want.
No, so, Daniel.
Yes.
Now it's time to celebrate you with a hooray. And it should be 3 times because we are so close to Denmark. In Stockholm, they have 4. So, for the new doctor, hooray, hooray, hooray.
Bravo.
Also in Bolivia, I hope.
Yes. Yes. Está rico. Házmelo. Ahora sí. Para mí el que puede ser otro. Ese es un calienta de 2000. ¿Qué dice este cromador?
Yes, it's fascinating today. We are present in 2 hemispheres.
Yes.
There are no more hemispheres to be present in.
Synchronized. I think we will still synchronize.
It could be done.
It's cool.
Felicidades, Daniel. Ahora estilo boliviano.
We have some, no, that's not visible. There are some nuts you can taste directly from.
Ah, okay.
En liten stund till. En liten stund till.
Radar seems very important.
Sí, por favor. No se escape, que hay más. Ahora tienes que abrir mi vino.
De repente por el contacto. Este ladito
Por favor. No, no se preocupen. Mira cómo está un tallazo explicando igual.
The only time I came to
Danielito.
Al medio.
Nu efter måndag, innan vi hade småbarn, men nu studerar vi.